Hi, I'm Raul Murillo from the Complutense University of Madrid, and I am presenting our paper, Energy Efficient Mag Units for Fused Posit Arithmetic. I will start introducing Posit Arithmetic. It was designed as an alternative to floating point standard in 2017. Posit formats are defined with two parameters. The first indicates the total bit length, and the second, the number of bits for the exponent. The Posit format consists of 4 fields. The first bit indicates the sign. Next, we have a new field called regime, which has no fixed length, but consists on a sequence of identical bits that encodes a scaling factor. Then we have the exponent, and finally, there are some fraction bits. So the value of a common Posit number is given by the following formula. Posit arithmetic has many interesting properties. First, it doesn't use a lot of bit patterns to represent not a number of sections, but uses a single representation for 0 and not real values. Also, under the same bit width, Posit arithmetic provides both larger dynamic range and higher precision than standard floating point numbers. Finally, the standard for Posit arithmetic includes fused operations, in which intermediate results are not rounded, but they are accumulated into a larger register called quire. The fused Posit operations are one of the main ideas in this work. As already mentioned, this kind of operations refer rounding until the last operation, which can reduce the error of large computations such as dot products or matrix multiplications. To do that, the intermediate results are accumulated into a larger register called quire. As seen in this figure, the quire is a kind of fixed point accumulator with some extra carry bits that allow to perform accumulations with no risk to overflow. This table lists the total size of the quire accumulator when using different Posit parameters. To assess the performance of Posit function fused operations, we selected deep neural networks as use case. In this scenario, we wonder if fused operations can mitigate the accuracy drop when performing post-training quantization. For that purpose, we used Depensive, which is a framework that allows to perform both inference and training of DNNs using Posit arithmetic. As shown in this table, when using 8-bit posits for inference, the accuracy of the models suffers some degradation. However, if using fused operations to perform matrix multiplications within DNNs, the accuracy remains similar as in the baseline models while reducing their size in a factor of 4. On the other hand, we propose a design for Posit fused multiply and accumulate units. This unit requires 3 inputs. 2 of them are posits, and the third one is the value to be accumulated. At the first step, the posits must be multiplied. Then the intermediate result must be shifted into a quire format before performing the addition. It must be noted that this unit does not perform rounding, but the quire to Posit conversion is done only when the whole computation is finished. The quire accumulator can be large, and we realized that the final quire adder is the most resource-demanding component. In fact, the delay of the whole unit is governed by this component. Then, in this work, we compared different designs for performing quire addition. In particular, we compared the ripple carry adder, which is simpler but slower than other designs, with the brain count adder, which can perform additions in logarithmic time with a small area overhead, and the Covey-Stone adder, which is the fastest design, but requires much more area than the others. This is proven by the data in the graph, which shows the synthesis results normalized with respect to the ripple carry adder. The proposed designs are implemented into the Flopoco tool, which allows to generate parameterized units for any POSIT bit width or even modifying the total required size. The generated results, which are available online, are compared with previous implementations. For that, we perform cell synthesis using Synopsys Design Compiler. As can be seen in this plot, for this case, the MAC unit that uses triple carry order design requires less area and energy than previous implementations. In addition, the energy consumption can be further reduced by replacing the design of the acquired adder with the Brent Kahn or the Cookie Stone designs. To sum up, in this work, we evaluated the performance of POSIT fused operations in deep neural networks, where the 8-bit POSITs using fused operations provided similar results as the 32-bit formats. Also, we proposed a design for fused POSIT multiply and accumulate units. The design is completely parameterized and is also integrated into the Flopoco tool. We also compared different variants for performing quire addition, including triple carry, Brent Kahn, and Cookie Stone adders. With respect to previous implementations, the proposed designs reduced energy and latency in more than 83%, with a slight increase in area of about 4%. Here concludes the presentation. Thank you for your attention.